Hello everyone. Today we'll discuss about operations on real numbers. We learned in earlier classes that rational numbers satisfy the commutative, associative, and distributive laws for addition and multiplication. Moreover, if we add, subtract, multiply, or divide except by 0 two rational numbers, we still get a rational number. That is, the rational number are closed with respect to addition, subtraction, multiplication, and division. It turns out that irrational numbers also satisfy the commutative, associative, and distributive laws for addition and multiplication. However, the sum, difference, quotients, and products of irrational numbers are not always irrational. For example, root 6 plus minus root 6, root 2 minus root 2, root 3, dot root 3, and root 17 by root 17 are rationals. Let us look at what happens when we add and multiply a rational number with an irrational number. For the root 3 is irrational, what about 2 plus root 3? That is 2 root 3. Since root 3 is a non-terminating, non-recurring decimal expansion, the same is true for 2 plus root 3, that is 2 root 3. Therefore, 2 plus root 3, 2 root 3 are also irrational numbers. Check whether 5, 7 root 5, 7 by root 5, when root 2 plus 21, pi minus 2 are irrational numbers or not. Root 5 is 2.236 dot dot dot. Root 2 is equal to 1.4142 dot 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 by 3.1415. Then 7 root 5. Then 7 root 5 is equal to 15.652. That is, and 5 by root 5, 7 root 5, 5 into root 5, that is 7 root 5 by 5, 3.1304. Root 2 plus 21, that is 32.4142, pi minus 2, that is 1.1415. All these are non-terminating, non-recurring decimals, so all these numbers are irrational numbers. Now let us see what generally happens if we add, subtract, multiply, divide, take square roots and even nth roots of these irrational numbers when n is any natural number. Let us look at the example. Add 2 root 2 plus 5 root 3 and 2 root 2 minus 3 root 3. Let us add 2 root 2 plus 5 root 3 plus root 2 minus 3 root 3. That is, we are getting root 2, 2 root 2 plus root 2 plus 5 root 3 minus 3 root 3. That is 2 plus 1 root 2 plus 5 minus 3 root 3. That is 3 root 2 plus 2 root 3. Multiply 6 root 5 by 2 root 5. That is 6 root 5 into 2 root 5. 6 into 2 into root 5 into root 5. That is 12 into 5. That is 60. Divide 8 root 15 by 2 root 3. Then we are getting 8 root 3 into 5 root 5 by root 3, 4 root 5. These examples may lead to you expect the following facts which are true. The sum or difference of a rational number and irrational number is irrational. The sum or difference of a rational number and irrational number is irrational. The product and quotient of a non-zero rational number with an irrational number is irrational. If we add, subtract, multiply, or divide two irrational numbers, the result may be rational or irrational. Right? We now turn our attention to the operation of taking square roots of real numbers. Recall that if a is a natural number, then root a is equal to b, means b square is equal to a and b is greater than 0. The same definition can be extended for positive real numbers. Let a is greater than 0 be a real number, then root a equal to b, means b square equal to a is greater than 0. In this section we saw how to represent root n for any positive integer n on the number line. We now show how to find root x for any given positive real number x geometrically. For example, let us find it for x equal to 3.5. We find root 3.5 geometrically. Make a distance of 3.5. Here you see this is 3.5, right? 3.5. Take BD equal to 3.5. That is 3. BD is equal to 3. This is AB. We have taken 3.5, right? Here you see that is also, if we take x, this BD is root x, right? This value, right? Now we find that. Notice that in figure, triangle OBD in this triangle, the right angle triangle, then the radius of the circle is x plus 1 by 2. This is x plus 1 by 2 units. Therefore OC is equal to OD. OC is equal to OD equal to OA x plus 1 by 2 units. The OB equal to x minus x plus 1 by 2 x minus 1 by 2. So by Pythagoras theorem we know that BD square, you see BD square is equal to OD square. BD square is equal to OD square OD square minus OB square. It is x plus 1 by 2 whole square minus x minus 2 whole square 4xy, that is x, right? So this shows that BD is equal to, this is root x, right? This construction gives us a visual, geometrical and geometric way of showing that root x exists for all real numbers x greater than 0. We want to know the position of root x on the number line. Now let us treat the line BC. Let us try the line BC as the number line with B as 0, C as 1 and so on. Draw an arc with center B, and radius BD which intersects the number line in E. Then the E represents the root x. E represents the value of root x. We would like to know now extend the idea of square root up to cube roots, fourth roots and in general for nth roots where n is the positive integer. Recall your understanding of square roots and cube roots from earlier classes. What is cube root of 8? Well, we know that it has to come to be some positive number whose cube is 8, and you must have guessed that cube root of 8 is 2. Let us try cube root 5 root of 5 243. Do you know some number b such that b to the 5 243? The answer is 3. Therefore 5 to the root 243 is 3. From these examples, can you define root a to the power n for any real number a greater than 0 and positive integer n? Let a greater than 0 be a real number and n be a positive integer, then cube root of n root of a is equal to b and b to the power n equal to a and b is greater than 0. Note the symbol root is used for square root, cube root, n root, etc. and called the radical sign. N is called the radical sign. We now list some identities relating to square roots which are useful in various ways. You are already familiar with some of these from your earlier classes. The remaining ones follow from the distributive law of multiplication over addition of real numbers and from the identity x plus y and x minus y, x square minus y square for any real numbers x and y. Let n be positive real numbers, then root ab is equal to root a into root b, root a by b is equal to root a by root b, root a plus root b minus into root a minus root b equal a minus b, root a plus root b a minus root b equal a square minus b, root a plus root b into root c plus root d equal to root ac plus root ad plus root b plus root bd, root a plus root b whole square equal to a plus root 2ab plus b. Let us look at some particular cases of these identities. Let us find the various identities here. Simplify the following cases: 2 plus root 7, 2 plus root 5. You multiply this one, 5 to the 10 plus 5 root 5 plus 2 root 7 plus 30 root 35. Root 5 plus root 5 into 5 minus root 5, 5 square minus root 5 whole square, 25 minus 5, that is 20. Root 3 plus root 7 whole square equal to root 3 whole square plus 2 root 3 into root 7 whole square is 3 plus 2 root 21 plus 7, that is 10 plus 2 root 21. Root 11 minus root 7, root 11 plus root 7, that is root 11 whole square minus root 7 whole square, that is 11 minus 7 is equal to 4. Note that simplify in the example above has been used to mean that the expression should be written as the sum of a rational and an irrational number. We end this section by considering the following problem. Look at 1 by root 2. Rationalize the denominator 1 by root 2. We now write 1 by root 2 as an equivalent expression in which the denominator is a rational number. We know that root 2 into root 2 is irrational. We also know that multiplying 1 by root 2 is equal to 1 by root 2 into root 2 into root 3 is root 2 by 2. In this form, it is easy to locate 1 by root 2 on the number line. It is halfway between 0 and root 2. Rationalize the denominator of 1 by 2 root 3, that is 1 by 2 root 3 into 1 by 2 minus root 3, 2 minus root 3, that is 2 minus root 3 by 4 minus 3, that is 2 minus root 3. Rationalize the denominator 5 by root 3 minus root 5. You have to multiply root 3 plus root 5, root 3 plus root 2, rationalize 5 into root 3 plus 5 by 3 minus 5, that is 5 minus 5 by 2 into root 3 plus 5. Rationalize the denominator of 1 by 7 plus 3 root 2. 7 plus 3 root 2, 7 minus 3 root 2 by 7 minus 3 root 2, 7 minus 3 root 2 by 49 minus 18, 7 minus 3 root 2 by 81. So, When the denominator of an expression contains a term with a square root or a number under a radical sign, the process of converting it to an equivalent expression whose denominator is a rational number is called rationalizing the denominator. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.